Hi everyone. I want to take a look at some of the projectile motion experiments that we did in class today. Just kind of review everything that went on. So if we can imagine, this first experiment is what's called a ballistics cart. So here's a picture of that cart, and basically you can see that long cylinder in the middle. There's a spring in there, and so to begin, the spring is loaded with a ball on top of it. And if we can get the cart moving pretty fast on this horizontal track that we have set up here, we're going to have a remote control that can then release the spring. And my question for you would be, all right, well, is the ball going to end up back in the cup, in front of the cart, or behind the cart? So let's see what happens. So in the video, we have the cart at different speeds in the horizontal direction, and regardless of those speeds, what happens is the ball always ends up back in the cart. So the second observational experiment involves a person, and this is one of my physics professors, Eugenia, in this particular video. In class today, you guys had me here on rollerblades. But if we have a person rollerblading and they launch a projectile, which in this case is going to be a basketball, what ends up happening in terms of where that projectile lands? So instead of a spring this time, we have this person's hands that will launch the projectile. And I think that video is pretty interesting as well, because the person in the basketball have an initial velocity in the x direction in the horizontal, and then only the basketball has a velocity in the y direction once it's released. Yet it still ends up exactly where the person is. And so we had a lot of students giving us some ideas in class today about why that would be. And somebody came up with the idea that, all right, maybe what happens in the horizontal in terms of velocity and acceleration is independent of what's happening in the vertical in terms of velocity and acceleration. So we decided that if that were true, we'd need to set up a testing experiment to test this idea. So what we have here is a very similar testing experiment to what we ended up deciding on in class. And this is an apparatus that allows for, you have two projectiles. One of them is just going to be dropped. And at the same time, the second projectile is going to be shot. And when you have a projectile that's being shot, it has a very high velocity in the x direction. This projectile that's just dropped has no velocity in the x direction. And if it's true that what happens in the x doesn't affect what's happening in the y in terms of motion, then because they're being dropped from the same height with an initial velocity in the y direction of 0, then they should both fall at the same time. If the fact that one of them has an x velocity matters, then they wouldn't fall at the same time. And so similar to what we found in class today, both objects fall at the same time, supporting our idea that vertical motion and horizontal motion are independent of one another. So if we take this idea that vertical motion and horizontal motion are independent of one another, this is really probably the biggest idea in terms of our study of projectile motion. So if we know that horizontal motion and vertical motion are independent of one another, how can we analyze problems that involve motion in 2 dimensions? So for example, if I have a dart gun, who doesn't like a Nerf dart gun, and I have a projectile being shot out of the Nerf dart gun, let's imagine that when I hold the gun, I hold it parallel to the floor. So I can imagine the path of the projectile looking something like this relative to the floor. At any point in this parabolic path, what would the force diagram look like for that particular projectile? So assuming that there's no air resistance, what would be touching the dart once it leaves the gun? Nothing. And then any field forces exerted on it? Sure, yeah, force of earth on it. So when I consider forces directed on this object, there's only one, and that happens to be force of earth on the object. So the net force in the x direction is nothing, and the net force in the y is mg. So knowing this, we know that net force in the x is nothing, but net force in the y is mg. And if this is the case, acceleration in the x direction will be 0, and this is assuming that there's no air resistance, no other objects interact with our object here. And acceleration in the y is 9.8 meters per second squared downward. Okay, so let's take these ideas that horizontal motion and vertical motion occur independently, and let's apply it to some quantitative problem solving. So imagine we have this Nerf gun, and the initial velocity of the dart as it exits the Nerf gun is 5.5 meters per second. Is that velocity in the x, or is that velocity in the y? Or is it some velocity at an angle to the x-axis? Well, in this case, this projectile is shot exactly horizontally. So this velocity, 5.5, is actually velocity in the x direction. So I'm going to name this velocity initial, the subscript 0 here for initial, and then x. So velocity initial in the x is 5.5. I think then that begs the question, what's velocity in the y then? Velocity initial in the y. Well, if all of the velocity in the initial state is shown within this vector, velocity in the y is 0 initially. Now we know from our study of kinematics that what's going to happen to this object over time in the y direction, well, that initial velocity of 0 is going to increase by 9.8 meters per second every second. For us, we're going to estimate this acceleration in the y direction to be 10. And I think that before we start this problem, we might want to assign a coordinate grid. So I'm going to make down negative, up positive, right positive, and left negative. That makes our acceleration negative 10 meters per second squared. Acceleration in the x direction is a bit of a different story here. Because there is no net force in the x direction, our acceleration will be 0 meters per second squared. And when we study projectile motion, if we have a true projectile where the only force exerted on it is the force of earth on it, then these two accelerations are always going to be true. Imagine that we want to find out where this projectile lands relative to where it started. So basically its displacement in the x direction. And we know that the height from which the projectile is launched, so basically the height at which you hold the Nerf gun, which will also be the bullet's displacement in the y direction, let's say we know that that's about 1.5 meters. And we want to find delta x in the x. Well, there's a small trick that that I have my students adhere to, especially when we're beginning our study of projectile motion. And what it is it's a chart that separates the x components, the x values, from the y values. So it's this t-chart here. The most important part of the t-chart is time. And I like to box in the time here to remind us that the time in the x and the time in the y will be the same because it's the same event. It'll take the projectile the same time of flight in the x and in the y. Nothing else, though, can cross this middle green line. Every other quantity is independent. So we have acceleration, velocity initial in the x, velocity final in the x, and the displacement in the x. And this is what we're looking for in this particular problem. Those same values are mirrored on the y, acceleration in the y, velocity initial in the y, velocity final in the y, and delta x in the y. And now that we think about this problem, we want to fill in any values that we know. Values that will always be the same for these projectile problems as long as the only force exerted on the object is mg, is force of earth on it. It's acceleration in the x being 0 and acceleration in the y being 9.8 or about 10 meters per second squared towards the ground. So I made downward in the negative direction. That's why this acceleration is negative. V initial in the y in this case is 0. V initial in the x in this case is 5.5. Because there's no acceleration in the x direction, the value for V initial and the value for V final in the x will be the same. And the delta x in the y is a given quantity in this problem. So the bullet falls 1.5 meters down. So this again is negative 1.5 meters downward. And we're trying to find delta x in the x. So how do we go about doing that? Now that we have all of our values set up in our t-chart, we need to go shopping for a math model that'll work for the quantities that we have and for what we're looking for. So over on the right here, I have our kinematics equations, and it's the same kinematics equations that you used in one-dimensional motion. And when it comes to projectiles, we'll just apply equations in the x for x quantities and equations in the y for y quantities. And if we're able to find the time for one side of our t-chart, that time can go over to the other side of the t-chart and help us find any missing values there. So let's start with some type of y analysis. I have acceleration and v initial and delta x in the y. So I think I'd be able to find time if I use this first equation here. So I'm going to set this up. This 0 meters per second times time, anything times 0 is 0, so that's basically going to go away. I have my room over here, times d squared. So I end up with 1/2 times negative 10 is negative 5 meters per second squared times t squared. I'm going to divide both sides by negative 5 meters per second squared. So 1.5 divided by negative 5 is 0.3, and the units on this are seconds squared. I'm not interested in t squared. I'd really like just t, so I'm going to take the square root of each side and end up with t is equal to about 0.5 seconds. So now that I have time, I actually have time on the x side as well. So in order to find delta x, I'm going to use the same equation, but for all of my x values. Because acceleration in the x is 0, that whole term goes away, and I can easily find delta x in the x by taking my 5.5 times 1/2 seconds, giving you 2.75 meters.